Students have joined already. Okay. Yes. So today we are starting this subject, artificial intelligence, and the subject is also very, very important as per your GATE exam point of view. So first of all, let's see the syllabus first. So this is the syllabus for AI. So you have this search, that is three types of search are there in the graphs, that is that is informed, uninformed, and adversarial. So basically, this topic will be covered by Sachin sir. Okay. And this logic, prepositional logic, and predicate logic, this topic I will be covering. Okay. But we are starting today with this topic, that is reasoning under uncertainty. So first, we are going to cover this second half of this syllabus of AI. And then I will be covering this one. And along with this parallelly, Sachin sir will be covering this also. Okay. So your entire subject will be completed. Fine. Right. So let's get started. Reasoning under uncertainty. So when we talk about uncertainty, what do we mean by uncertainty? Uncertainty means we are not certain about certain event, right? We are not sure about a certain event, whether it is going to happen or not. So it's kind of, we basically believe or we calculate, some kind of probability that, okay, this much percentage is the chance for happening of a certain event, right? So that is our uncertainty. So basically we calculate the probability, we calculate the percentage of chances of happening one event, right? So to understand this topic in a much better way, or you can say in the best way, we need to first cover this few prerequisites for this certain topic, and that is nothing but the probability basics. Okay. So I know that you have already covered probability. Sachin sir has already covered probability in a lot of detail. But for someone who is, who is learning this subject, it is very important to just brush up all the details of all the basics of probability. And I will be covering few questions as well, so that you can get, it will be a kind of, quick revision of probability, or all those topics which are required for this particular topic. Okay, reasoning under uncertainty. Is this clear? Good evening, Sneha. Okay, so let's get started. So let's see the motivation first. Why do we even talk about this, reasoning under uncertainty? Why do we need it, and what we actually do in this one? So for that, we need to understand the motivation first. So let's say maybe one of you are traveling to airport, and what you do is you leave 10 minutes before the flight, right? So you kind of estimate it. Let's say I'm leaving 60 minutes before the flight time, or maybe 180 minutes, or maybe 3 hours before the flight time, the scheduled time. Okay. So don't you think that if you are leaving for airport from your home, then there is certain kind of uncertainty, right? So as it is mentioned here, that uncertainty is everywhere, right? Good evening, Sumit. So uncertainty is everywhere. So this is the example that you can consider here. So if you are leaving 10 minutes before the flight, right, to reach the airport, so what kind of problems that can occur? There can be many kind of problems, right? There is something we called as partial observability, that is road state. It depends, how good is the road, whether you are going through highway, or whether you are going through some road which is in the bad state, right? So it also depends on that. It also depends on the traffic, right? How much traffic is there? So, and apart from that, certain unfortunate events can also happen. Maybe the tire got flat, right? There is a puncture, so due to that also there will be a delay, for you in reaching the airport yeah, you can say in reaching the airport on time. Yes or no? So many kind of uncertainty is there. And when many kind of uncertainty is there, you cannot apply the logic, right? You cannot directly just say, okay, I will reach on time, or I will not reach on time. Are you getting this point or not? When the logic cannot be applied, the exact logic cannot be applied, there we have something called as degree of belief. There we have something called as degree of truth, right? where we calculate the chances whether I will be reaching on time or not. Are you getting this? So if you are moving from certain source to destination, right, then if you don't consider these uncertain events, then it is quite easy, right? That, okay, this is the shortest path and from source to destination, you can reach on time. But in reality, in practical life, we have uncertain events. We come across lots of uncertain events, which we have to consider, right? We cannot avoid them. Yes or no? Correct. So these are certain kinds of events that you have to consider when you are going from one source to destination, right? Similarly, there are thousands of examples, or you can say in day-to-day life also we deal with uncertainty, right? So so we need to consider it. We have to consider it. And in order to, let's say, let me give you one more example. Let's say you have built one robot, okay, or maybe you have built one, let's say, driverless car, self-driving car. Now, in self-driving car, if you are not going to consider the possibilities or the obstacles that you can come across, then it is very easy. But in practical life, there will be a lot of obstacles, right? Maybe from your side, one more car is coming, and maybe it can hit the self-driving car, or maybe some obstacle is there, right? So there can be many possibilities. So uncertainty is everywhere, right? And we have to deal with it. So how AI is going to deal with this uncertainty, uh, which cannot be, you can say, just by using the logic, you cannot, deal with it. There is something beyond the logic, right? Is this clear so far? This motivation, why we need to consider these scenarios where uncertainty is there? Because in real life, if you see all the examples, if you see all the real life examples, uncertainty is there, right? Even if you talk about the actual fact, that is the life is also uncertain, right? You know that death will definitely come, but you don't know when it is going to come, right? So that is also uncertain. Is this clear? Any doubt, anyone? Okay. So just to give me a response whether you are getting it or not, just you can give me the thumbs up in the reactions. That is also sufficient for me, okay? So that I can understand, okay, you are getting it or not. Okay, fine. You don't have to even type again and again. That is fine. Cool. So there are many types of knowledge representations. So when I say knowledge representations, that means if certain statements are given to you, right? So what kind of language will be applicable on that statement? For example, let's see here. There are many types of knowledge representations. So many types of languages are there. So one is your prepositional logic. That is also part of your AI syllabus, which we will be covering after covering this, this entire topic of uncertainty. Okay. So there is one propositional logic. So the main elements of this propositional logic is facts. Only facts are there. For example, if I say it is raining, so what will be the what you can assign to this particular statement? You can say, if you are saying that it is raining, so you will be saying that yes, it is true. And if it is not raining, you will be saying it is false. This statement is false, right? So when I say propositional logic, that means it can have either true or false. Mainly they can have these two values, but unknown can also be there. Right? But there is no uncertainty. If I'm saying it is raining, do you think that there is uncertainty in this event or in this fact? No, right? Either you are going to say that, okay, it is true that it is raining, or you are going to say that it is false. Or maybe if you are not present at that particular location, maybe you can say that I don't know, right? That can also be one of the assignment to this particular statement, right? So, but there is no uncertainty in this propositional logic. The first one does not represent uncertainty. The second one is first order logic. I will be giving you examples for all these. Don't worry about it. So the second one is first order logic. When I say first order logic, you have facts, you have some objects, maybe a person, maybe any kind of object can be there, and there will be some relation between those objects. Okay, again, to this first order logic, the assignments that you can do, that you can give to the statement will be true, false, or unknown, right? And then we have temporal logic. Then we have, so basically in temporal logic, you have facts, you have objects, you have relations, but time is also there. So some time will also be there. Okay, so you can see that in all these first three, the first three languages is not having any kind of uncertainty. But if I talk about the rest three, that is temporal CSP, that means some constraint is attached to the time, right? And then we have fuzzy logic. So I will be giving you the example for this one also. And then we have probability theory. To all these last three, uncertainty is there. So let's understand through examples. It will be very easy for you to understand. Let's see this one by one. So carefully see this. So here are some examples of each type of knowledge representation language. So the first one is propositional logic. When I say propositional logic, mainly you have two assignments, that is true or false. As I told you that it is raining, so you will be saying true or false. The light is on, you will be saying true or false. Now just tell me, do you have any kind of uncertainty in these statements? Yes or no? No, right? Like clearly there is a certain thing that you can say whether it is true or false, right? And for some statements, maybe you can give unknown, right? That means you don't know, simply. Now if I talk about first order logic, so let's see the example of first order logic. When I say all humans are mortal, right? And the second statement is, it is given to you that Socrates is a human, therefore Socrates is mortal. So can you see, in propositional logic, you have just facts. But in first order logic, you have facts, you have objects, you have relations between those objects, right? And again, you can assign true, false, or unknown. So basically in first order logic, we will be covering this in a lot of detail because these two are there in your syllabus. We will be covering that, as I told you, after this uncertainty topic. So in this first order logic, we use basically quantifiers, that whether it is applicable for all or whether there exists some person for which the relationship that we are describing, between the objects, whether it is true, false, or unknown. So these quantifiers will be used in first order logic. Is this clear to all of you so far? Do you have any doubt? Just let me know. Clear now? Okay. Let's proceed further. And now let's talk about temporal logic. So what is temporal logic? Let's see the example. The train will arrive at 5 p.m. The train will arrive at 5 p.m. Now again, to this statement, either you can say it is true, or you can say it is false, or you can say maybe, I don't know, unknown, right? Similarly, it will always be the case that the system remains secure. So basically in temporal logic, we mainly talk about the statements mainly deals with time and the order of events. Okay. So again, you can have true, false, or unknown, but there is no uncertainty here. But when you have temporal logic is there, but along with that, you have constraints satisfaction problems. That means you attached some constraints, some conditions are attached to those logics. Then you have some kind of uncertainty. For example, if I say task A must be completed before task B and both must be completed by 3 p.m. So now here you have certain kind of uncertainty. And what can be the assignments here? So if you see here, the assignments that we can have is time intervals, right? So here you don't have something called as true, false, or unknown. No, that is not there, because you can just read the statement here, right? Task A must be completed before task B and both must be completed by 3 p.m. right? So certain kind of time interval is there, but can you say it is true, false, or unknown? No, it is just a statement with some constraints attached to it. Similarly, the second example is class schedules need to be set such that no student has two classes at the same time. Again, some kind of condition is there that you need to make the schedules of the class in such a way that no student should have collision. You can say no student should have two classes at the same time, right? So again, you cannot assign true, false, or unknown here, right? Clear? So this problem deals with constraints involving time intervals or specific time points. Is this clear? Any doubt so far? So these are the various type of languages that we have for knowledge representation. Now let's see the last two. One is fuzzy logic. So let's see the example here. Fuzzy logic means it is not it is unclear, or you can say it is not partially true, partially false, something like that. For example, if I say the weather is somewhat warm today. Now let's say if I say to you the weather is somewhat warm today. Now it may also happen that for you it is not warm. Yes or no? For someone else it is not warm, but for me it is warm. So can I say it is some kind of clarity is not there? Maybe it is partially true. Yes or no? So fuzzy logics basically deals with degree of truth. How much you can say the percentage of truth, right? Exactly. It is relative. You can say it is relative. For someone it is true. For someone it is maybe partially true. For someone it is maybe false. So it is kind of degree of truth, right? So basically you can say how much percentage of truth is there in that particular statement, right? Similarly, the likelihood of this food being spicy is medium. It may happen that for me that food is spicy or medium spicy, or for someone else it may be more spicy, right? So you cannot give true, false, or anything like that, but you can definitely assign degree of truth, right? Degree of truth can be assigned to fuzzy logic. So fuzzy logic deals with degree of truth, where statements aren't just true or false but can be partially true. Is this clear? So again, can I say some kind of uncertainty is also present over here? Yes or no? Correct. But when we talk about AI, so mainly we talk about the probability. Mainly we deal with probability theory. Okay. For example, if I say there is a 70% chance of rain tomorrow. Now, again, this is uncertain. It may happen or it may not happen, right? So some chances are there. So for this one, you have degree of belief. For probability theory, we basically deals with degree of belief, right? If you are tossing a coin, whether it is going to be a head or a tail, that is again degree of belief. Or you can say the chances or probability of tossing a coin and getting a head is 50%, 1/2. Clear? So degree of belief is there. Let me give you one more example. Let's say you have designed one robot, right? And you have designed that robot in such a way that it can, identify certain objects. Maybe you want that robot to basically identify some glass, let's say some object, let's say glass of water, right? So now first it is going to identify where it is present. Okay, let's say you have placed that glass in front of that robot. Now first of all it will see the location, right? So again, can you see that there is some kind of uncertainty? Maybe it may happen that instead of picking up the glass, it may pick some other object, right? It may also happen. Or maybe if it tries to hold that glass, it may also happen that it does not hold it correctly, right? Or maybe it may fall down. So there are lots of uncertainty when you are dealing with AI. When you talk about AI, so for some AI problems, directly logic can be applied. But for some AI problems, those where the events are uncertain, where you have uncertainty, then you cannot just directly apply the logic. Then you need to find the probabilities. Then you have to deal with the probabilities. Then you have to find how much, you have to find the chances of certain event happening. Are you getting this point or not? Is this clear so far? Again, some more examples are given here. The probability of drawing a red card from a deck is 50%. So that is true. I mean, that is there, but again, point is, you are like if you are picking a card, if you're drawing a card and it should be a red card, so definitely it is 50%. Like half of the cards are black and half of the cards from the deck is black or red and black, right? So again, it is 50%. So again, you have to deal with this degree of belief. You have to deal with this uncertainty using this degree of belief, or you can say in other words with in terms of probabilities. So is this clear? These are the various languages. These are the various languages of knowledge representation. Now, if you have any doubt so far, you can ask. Any doubt, anyone? And as I told you that the first three do not represent uncertainty, while the last three do. Because when you can clearly say it is true, false, or unknown, that means there is no uncertainty about it. Clear? I hope it is clear so far. Shall we proceed now? Okay. Fine. So the same thing is mentioned over here as well. You can just read it out later on. So now, before even starting, before even understanding what is uncertainty, and before what are the have, that we can use to, in these kinds of events where we have uncertainty. So for that, we need to understand, or we need to just brush up our probability basics. So in this class, we are going to talk about now probability basics. In the next class also, in 1 or 2 more classes, we will be covering those prerequisites, I can say. And that will definitely help you going forward. That will definitely help you. Even if you have covered the probability already, still it will help you a lot. Okay. So let's get started. Now, the first thing, let's see the few basics, and then we are going to proceed towards the next terms. So I hope all of you are aware of what is sample space, right? The set of all the possible outcomes. Let's say if I'm throwing a die, right? If I'm throwing a dice, then all the set of possible outcomes from 1 to 6. Can I say this is my sample space? This is my sample space. Yes or no? Right? So beginning with a set, you can just name it as S also. You can say just a row also, called just a denotation, nothing else. So this is a sample space. Sample space is a set of possible outcomes. Now each W belongs to this sample space is a sample point, right? That means you can say possible world or atomic event. For example, if you are rolling a die, you know that these are the possible outcomes you can have from 1, 2, 3, 4, 5, 6. It can be anything, right? So if I say, so basically how many outcomes are there? 6 outcomes are there in the sample space. Now, if you assign, if I want to find a probability of W, and W can be anything. Let's say, for example, if I ask you simply, what is the probability of finding an odd number? If I'm rolling a die, what is the probability of getting an odd number? So what will be the probability? Anyone? If I'm throwing a die, what is the probability of getting an odd number? Yes, it's 1 by 2, simple, right? Why 1 by 2? Because we know the odd numbers, either it can be 1, or it can be 3, or it can be 5. So there are three possibilities of odd number, right? So it can be any of these. So if I say, if A is an event and that event represents, getting an odd number while throwing a die, so it can be, how many possible outcomes are there? That is 3. And out of total sample space, right? So it is going to be 3 by 6. So this is going to be the probability that, or you can say 1 by 2 also. This is going to be the probability of getting an odd number while throwing a die. Is this clear? So the same thing is mentioned over here, the probability space or probability model. So you take a sample space and you assign a number. So you are finding the probability of W here, and it can be, W can be any atomic event. For example, here also it is mentioned that for rolling a die, what is the probability of getting 1? That is 1 by 6. Probability of getting 2, that is 1 by 6. Similarly, you can find the probability of all these numbers is 1 by 6. An event A is a subset of this. So let's say they have assumed that there is one event A, and if they say probability of event is defined as follows, as you can see, probability of A is what? A can be any event. Let's say, as I told you, that it is getting an odd number. So that can also be one event, right? Or getting a number less than 4, as in this example they have clearly mentioned, though getting a number less than 4. So now getting a number less than 4, there can be 3 possibilities, 1, 2, 3. So what you do, you basically sum up all those possibilities, or you can see the probability of all those events belong to A, right? So probability of rolling a die and getting a number less than 4, it is going to be P of 1 plus P of 2 plus P of 3. And what is the probability of getting 1 when you are rolling a die? That is 1 by 6. So 1 by 6 plus 1 by 6 plus 1 by 6. And finally, you are going to get the answer, that is 1 by 2. Is this clear? Simple stuff, right? These are very simple things. Okay. Let's proceed further. Now, let's talk about the random variables. So these are very important because we will be using these going forward also. So what is the random variable? Random variable is a function from sample points to some range, such as integers or booleans. Let me give you some example. So let's say if you're rolling a die, and if I say getting an odd number, so odd of W. Now this odd of W is what? You can say this is a kind of random variable that you are defining. So it is going to be true. This event is going to be true if W is odd. Otherwise, it is going to be a false, right? So if I say X is a random variable, see, random variable can be discrete, random variable can be continuous also, and random variable can be Boolean also. That means it can have the value true or false. It can have the continuous value also, and it can have a discrete value also. In this example, if I say that if X is a random variable, then probability of X is equal to Xi. Now it can be anything. Like for example, here it is saying probability of odd is equal to true, right? So here I can say this odd is a random variable. And what is the value here? That Xi that I'm saying, that is true here. So probability of odd is equal to true. So you are going to sum, you are going to take the summation of all those probabilities where the value of X, where the value of that particular W is Xi. So like in this example, if it is saying probability of odd is true, so probability of 1, probability of 3, probability of 5. That means all those probabilities where you are getting the odd number. So you are simply going to add them and you are going to get 1 by 2. Is this clear? Any doubt, anyone so far? Okay, fine. Now, propositions. So as we have taken just now, we have taken the example of odd number when you are throwing a die. So as I told you, this odd. Now, can this odd be continuous or discrete? No, right? Because we are simply defining the odd in such a way that either it is going to be true or false. When you are rolling a die, whether the number you are getting is odd or not, so basically it is going to have two values. So this odd is here, in this case, it is a propositional or Boolean random variable. So when I say Boolean random variable, that means it can have two values. When I say propositional, then also you can say it is same as saying as having two values, either true or false. So this is the range of this Boolean random variable. Clear? Now some simple things are also there here that they have mentioned. Whether when you are saying that a propositional random variable is true, you simply write them as P of odd. You simply write them as P of odd. But when you say that it is false, so you can represent like this: not of odd, probability of not getting an odd, which is nothing but probability of getting even number, right? So these are just some representations, nothing else, basic representations. Okay. Similarly, Boolean formula, this is also, I hope you know this, the disjunction of sample points in which it is true. So A or B. When I say A or B, this is disjunction. Disjunction, that means or, you can say. Either A is true or B is true, right? So when I say A or B, in that case, three possibilities can be there. A is false, B is true, or B is false, A is true, or both are true. Then can I say it is equivalent to A or B, right? Basically, if in digital logic we consider this, I know that you don't have that subject here, but just I'm saying you will be able to understand that. So if I say 0, 0, 0, 1, 1, 0, 1, 1. Now, if let's say this is A, this is B. Now, if I'm calculating A or B, so can I say the output that I'm going to get will be 0, 1, 1, and 1. So A or B means what? Either one of them is true, then it is true. If both is true, then also it is true. But if both is false, then the result will be false, right? If any one of them is 1 or true, then the result is true. The same thing is happening over here also, and the same thing can be applied in probability also, in terms of probability. So probability of A or B is nothing but probability of not of A or B, or, so basically or is replaced by plus probability of A and not of B plus probability of A and B. Clear? Any doubt so far? Okay, good. Now, as I told you that we have three types of random variables. So one is propositional or Boolean, right? One is discrete random variables where we can have finite or infinite values also. And other one we have is continuous random variables. Okay. So when I say propositional or Boolean, that you understood, right? Odd is equal to true or false. So it can have two values. For example, here cavity. If I talk about cavity, do I have a cavity in one of my teeth? So the values that you can assign, either it is going to be true or it is going to be false. So here cavity is equal to true is a proposition, right? Similarly, you can write in small words also, like in a lowercase also. So it implies that it is saying it is true. Clear? What about discrete random variables? It can be finite or infinite. For example, weather is one of these. Maybe weather is sunny or rain or cloudy or snowy, right? So weather is equal to rain is proposition, but it is not Boolean, right? Because you are not having the values like true or false. Clear? And the one of the major thing here, this line is very important. The values must be exhaustive and mutually exclusive. Do you know the meaning of mutually exclusive and exhaustive? Anyone? What do we mean by mutually exclusive and exhaustive? When I say mutually exclusive, what does that mean? We have mutually exclusive events also, right? Intersection is zero. Intersection is zero. Exactly. For example, just I'm taking this example, and then later on I will be talking about independence event and mutually exclusive events again. Then I will be giving you a different example. But just consider here this one, this example here. Weather is one of sunny, rainy, cloudy, or snowy, right? So here it is saying that values must be exhaustive and mutually exclusive. The simple way to understand is, if you take the intersection of all these values, so you have sunny, you have rainy, cloudy, and snowy, right? If you take intersection of all these, can I say the intersection of all these will be 5? Or you can say empty set, right? There is no intersection between this. There is no common value between this. So this is what it is saying. So whenever we are dealing with a discrete random variables, it has to be mutually exclusive. That means the intersection of the values is 5, or in other words, you can say there is no common values, right? So that means mutually exclusive. In terms of discrete random variables, we can say it is mutually exclusive like this, right? I'm not talking about the events as of now. What about exhaustive? Any idea? Exhaustive means if you take the union of all these values, or if you sum up all these values, or if you consider all these values, then it will be equivalent to the complete set of values you have. Like if I consider all these values, sunny, rainy, cloudy, snowy, so can I say now if I add all these values, if I take the union of all these values, I will be having the entire set. So in case of discrete random variables, this is what it means, that values must be exhaustive. It should not be like you are having these 4 values, but you are just considering these 3 values. It should not be like this, because these are not exhaustive. So we will be talking about these exhaustive and mutually exclusive just again, after some time in terms of events. Then you will be getting more clarity. I will be giving you more examples also. Okay. So this is what it means, mutually exclusive and exhaustive. And then we have continuous random variables also, which can be bounded or unbounded. Let's say if I say bounded, that means, for example, I can say temperature has to be less than 22. Then it is bounded. And It can be unbounded also, simply temperature is equal to 21.6. So this is continuous random variable. Clear? Again, the same thing is mentioned over here. Not of cavity means cavity is equal to false. And when we assign probabilities of propositions, so when I say probability of cavity is 0.1, then can anyone tell me what will be the probability of not cavity? If I say this is Boolean random variable, so it is simply going to be what? 0.9. Why? Because the sum of probability of cavity and probability of not cavity is equal to 1, right? So if probability of cavity is 0.1, so probability of not cavity will be equal to 0.9. Clear? Now, can I say the same thing here? Tell me this. Probability of weather is equal to sunny is 0.72. If I ask you what is the probability of weather is equal to rain, can I say it is 1 minus 0.72? What do you think? Can I say that? No. Why? Because these are not propositional random variables. These are not Boolean random variables. Here, whatever values you have, the sum, the probability of all these values will be equal to 1. Probability of all these, that means probability of weather being sunny plus probability of rain, weather is equal to rain, plus probability of weather is equal to cloudy, plus probability of weather is equal to snow will be equal to 1. Is this clear so far? Any doubt, anyone? I hope it is clear. So let's see some more definitions here. These are just these are very theoretical, I know, but after some time we will be solving questions also. So don't worry about it. Okay, just follow me. So syntax for probability distributions. So now here, so basically we are representing a discrete probability distribution as a vector of probability values. So when I say probability of, so basically this is the distribution, probability distribution. So we know that this is based on this vector. We can say probability of weather being sunny is 0.72, probability of weather is rainy is 0.1, and so on. For other weather also, the probabilities are there. So this is a vector of probability values. So you can say this is the distribution of these discrete random variables, and we can say these are representing discrete probability distribution. Clear? And here also it is clearly mentioned that above is an ordered list representing the probability of sunny, rain, cloudy, and snow. So probabilities of sunny, rain, cloudy, and snow must sum to 1 when the vector is normalized. If I say the vector is normalized, then definitely the probabilities has to be equal to 1. Okay. But if they are not normalized, then we can normalize it also. We will talk about it. If B is Boolean random variable, then it is very simple, right? Probability of cavity is equal to true is 0.1, then not of cavity will be equal to 0.9, right? This we know, this is very simple. Also it is mentioned when the entries in the vector do not add up to 1, when they do not add up to 1, but they represent the true ratios, then what we do, we basically add a normalizing constant, let's say alpha. So if I say P of cavity, if this vector is given to me, now if you add these two values, is it equal to 1? If you add these two values, no, right? They are not equal to 1. So what we do, we basically add this normalizing constant. So here the normalizing constant is 10. So if you add these two values, it will be equal to 0.1. So here we are basically multiplying with this normalizing constant. So now we can say it will be equal to 1. Just after multiplying by 10 into 0.1, it will be equal to 1. So we can normalize it also if they represent the true ratios. Okay, simple. Now let's talk about certain terms here. Any idea, anyone? What is marginal or what is simple probability? I hope you might have covered all these. So it is you can say it is why called as simple probability, because it is a probability of a single event. For example, if I toss a coin, let's say A is an event getting a head. A is an event where A represents that getting ahead when I'm tossing a coin, right? Tossing a coin. So if I have to find the probability of this, now apart from this, nothing else is given to you. So you are not going to consider any other events. Without considering any other events, then we simply say, what is the probability of A? What is the probability of A? That is going to be 1 by 2. Why 1 by 2? Because you know that it is equal to number of outcomes for this event A divided by number of outcomes, possible outcomes you have in, or total possible outcomes you have in sample space. So you know in sample space you have two possible outcomes, head or true, tail, head or tail, right? That means two are there. And for this one, only one possibility is there. So that is 1 by 2. Is this clear? So this is your marginal or simple probability. Let me give you one more example, or let's take one more example. And now you try to answer. If I say, let's say you have two red balls in a box. Apart from that, you have maybe 4 blue balls and 3 green balls. Now, if I simply ask you, let's say you have event maybe E, you have to find event E represents getting a blue ball from this box. So can you tell me what will be the probability of getting a blue ball when one ball is drawn from this box, or you can say bag? 4 by 9. How we can calculate? It is very simple, right? You can just simply say that 4 blue balls are there. So you can say 4 divided by total balls are there. That is 5 plus 4, that is 9. Or you can just more formally, you can also say that you have 4 blue balls. So out of 4 blue balls, you are going to select 1 blue ball, right? And in total balls, you have how many? 9. So it is going to be 9C1. So this way you are getting this thing. So anyway, you can just say, like, this is just more formal way of selecting a ball, 1 ball out of 4 blue balls. And this is selecting a ball, 1 ball out of all the 9 balls. So this is your total sample space. This is the number of possible outcomes for this particular event, getting a blue ball. So it is 4 by 9. Is this clear? So this is your marginal or simple probability. Now let's talk about joint probability. What is joint probability? As the name suggests, some kind of joint is being applied here, right? Some kind of joint is being applied here. Let's see what the definition says. Joint probability is the probability of 2 or more events happening at the same time. So 2 or more events happening at the same time. For example, if I say that there are 2 events, A and B, right? There are 2 events, A and B. Now, let's say A represents a card is drawn. A card is drawn, which is, let's say, heart. Okay. And B is an event. A card is drawn that is ace. Let's say these are the 2 events. Now, before even talking about joint probability, can you tell me what will be the probability of A? Anyone? A card drawn from a deck of cards is a heart. Is a heart. What is the probability? It is very simple. Let's do it here. So probability of A, that means drawing a card which is a heart, you know that there are total out of 52 cards. Total we have 52 cards, right? So total possible outcomes, sample space size, you can say that is 52. Out of 52, you know that 13 cards are those cards which is you can say heart cards basically. So there are 4. We have spade, heart, and again we have 2 more, right? So so I can say out of total 52 cards, 13 cards are heart cards, right? So this is going to be the probability of A. Similarly, if I talk about probability of B, so a card is drawn, that is ace. What is the probability of B? So out of total cards, that is 52, how many ace cards are there? How many ace cards are there? So we have 4 ace cards. So the probability of B will be 1 by 13. Simple, right? I hope all of you know. Clear? Now let's talk about joint probability. Now let's talk about joint probability. When I say joint probability, now I'm considering another event. Let's say I'm considering another event. Let's say event E. Event E represents card drawn is heart and ace. Now we need to find the probability of E. Now we need to find the probability of E. So let's say randomly you just draw one card from a deck of cards, and we need to find that the drawn card is heart and it is ace also. Then what will be the probability? Now understand this thing. This E is what? This E represents, can I say this E represents the intersection of A and B? Yes or no? Because now this A represents what? We know that this A represents that a card is drawn which is heart, and this B represents that a card is drawn which is ace, which is an ace, right? So this E represents both heart and ace. So this is a kind of intersection. So can I say this, that probability of E is nothing but probability of A intersection B, which is nothing but, how we can find the probability of A intersection B? That means the number of outcomes for A intersection B divided by number of outcomes in the total sample space, you can say. Correct? Now, what will be the number of outcomes that we can have for A intersection B? So total 13 heart cards are there, and we know that for in every like you can say for one heart, like if I talk about heart, so there is only one ace, right? Total we have 4 ace in 4 groups, right? So we can say that only one possible outcome is there. Out of 13, only one is there, right? And total we can say this total sample space is going to be 52. Is this clear? Any doubt, anyone? So this is what we call as joint probability, because 2 or more events are happening at the same time. So here A is also happening and B is also happening at the same time. So this is the concept of joint probability. This is the concept of joint probability. Any doubt, anyone? Crystal clear? Shall we proceed now? Okay, good. Now let's talk about the next term, that is your conditional probability. This is very, very important. Conditional probability. So what this conditional probability says, let's see the definition first. Conditional probability is the probability of an event occurring given that it is already given to you that some another event has already happened. If some another event has already happened, now you have to find the probability of a certain event. So how we can represent, let's see how we can represent first, and then we will see the example also. So let's say A is an event and B is an event. There are 2 events. And when I say conditional probability, let's say this B is an event which has already happened. B is an event which has already happened. Which has already happened. So I can say probability of, I need to find the probability of A given B. Now it is given to me that this B has already happened. Now we need to find the probability of A. Yes, any issues, any connectivity issue? Am I properly audible and visible? Please let me know once. No issues, na? Okay, maybe Sneha, there is some internet connectivity issue from your side. Please check your, or you can refresh it also. Okay, from my side it is working fine. Okay, so probability of A given B. So B has already happened, and now we need to find what is the probability of A. So how we can, so basically this conditional probability we can write like this. So it is nothing but P of A intersection B divided by P of B. Clear? Divided by P of B. Okay. Now let's take the same example of cards, and let's understand this, how we can find this conditional probability. Let's say B is an event. Let's say B is an event, and that says that a card is drawn. A card is drawn, or you can say a card drawn is heart, let's say. Now this event has already happened, right? Now there is one event A, a card drawn is ace. Now I want you to find out the probability of A, that is a card drawn is ace, given that it is a heart. It is a heart. So probability of A given by B. So I can write this is probability of A intersection B divided by probability of B. What is the probability of B? A card drawn is heart. That is nothing but 13 by 52. Yes or no? That is nothing but 13 by 52. And what is the probability of this? A intersection B. So this is nothing but 1 by 52. Yes or no? So we can say this is 1 by 52 divided by 13 by 52. So this is nothing but, this will cancel out. So 1 by 13 will be the answer. Is this clear? Any doubt, anyone? Now, if you observe carefully, can I say that if I'm writing P of A given B, so we know that it is P of A intersection B divided by P of B. Yes. Any mistakes? Yeah, Sumit. It is fine, no? Yeah, sure. Okay. So if you carefully observe, see this one. What is this? Can I say this is joint probability? Can I say this is joint probability? And can I say this is marginal probability? Right? P of B, you are not considering any other event. So I can also write it like this, that conditional probability is equal to joint probability divided by marginal probability. Yes or no? Any doubt, anyone? Correct? Okay. Is it clear so far? So we have discussed marginal probability, we have discussed joint probability, and we have discussed conditional probability. If you have any doubt, please ask. Crystal clear? Okay. Now let's talk about independent events and mutually exclusive events. How many of you know the difference between these two? Just tell me yes or no. Or you can just give me thumbs up also, so that I can understand how many of you. Because like majority of the students, they get confused between these two events. Right? So let's discuss these. What are independent events and what are mutually exclusive events? So when I say mutually exclusive events, these are the events that cannot occur at the same time. They can never occur at the same time. That's why we call them as mutually exclusive events. Let me give you one example. Let's say if I'm tossing a coin, right? Now, either you are going to get a head or you are going to get a tail. Can it happen that I'm getting both? No. If I'm tossing a coin only once, it cannot happen that you are getting both, right? So that is your mutually exclusive event. That is your mutually exclusive event, right? So if that is your mutually exclusive event, so can I say that probability of head intersection tail, can I say it is going to be 0? Because if you are tossing a coin once, getting both at the same time can never happen. That is not possible. So that is your mutually exclusive event. Is this clear? In simple terms, you can understand this, right? So it cannot happen at the same time. Both the events cannot happen at the same time, then they are mutually exclusive events. Okay. Okay, what about independent events? The name suggests they are independent. That means they are not dependent on each other. That means they can happen at the same time. For example, if I'm rolling two dice, or let's say if I'm rolling two dice at the same time, right? Or let's say maybe one after another at the same time, or you can consider one after another also. Yeah, let's consider at the same time. So getting a odd number in the first die and getting a even number in the second die, are they dependent on each other in any way? No, right? They are not dependent. Similarly, let's consider another example. If I'm tossing two coins, getting head in the first coin and getting tail in the second coin, are they dependent on each other? Again, the answer is no. They are not dependent on each other. So these kind of events are independent events. So for these kind of events, if I say, let's say rolling a die, let's say R1, that R1 represents that event, and getting an odd number, right? Intersection, rolling a die and getting an even number. So these are two different dice. These are two different die. Die 1 and die 2. So if I'm finding the intersection of these two, so it is going to be equal to what? R of odd. So you can say, let's say R1 of odd, and this is R2. So R1 of odd multiply R2 of even. Is this clear? Any doubt? So in case of independent events, their intersection will be nothing but multiplication of probabilities of these two events separately. Is this clear? So this is the basic difference between mutually exclusive events and independent events. In simple words, you can understand in this way. Let's see what it says. So here also, clearly the definition is mentioned over here. So I have added these screenshots, or you can say, screenshots from multiple standard resources, so that later on also you can just quickly read it and you can get more clarity. Is this clear? So this is all for your notes purpose, nothing else. That will really help you. So the difference between mutually exclusive and independent events. Mutually exclusive event, two events are mutually exclusive when they cannot occur at the same time. For example, as I told you, that either you are going to get a head or you are going to get a tail. When you flip a coin, you are not going to get both. And similarly for independent events, the occurrence of one event does not affect the occurrence of others. That is the reason why we call them as independent events. Clear? So for example, if we flip a coin two times, the first time it may show head, but the next time when we flip the coin, the outcome will be heads also. So both are independent of each other. Clear? So again, these things you can just give it a read and you will be understanding more clearly. But I hope it is crystal clear to all of you, right? Is it clear now? What are mutually exclusive events and independent events? Understood? Okay. Now let's talk about our last topic of today's class. That is your theorem of total probability, and we will be solving question also based on it. Okay. So what is theorem of total probability, or sometimes we also call it as law of total probability, right? I hope you know this, but let's cover it in detail. So what this theorem says, see, understand this thing. You know one thing, that if I talk about conditional probability, let's say if probability of A given B, you know it is equal to P of A intersection B divided by P of B. Simple. This thing we have already covered, conditional probability, right? Now let's understand this. Let's say A is an event. A is an event caused by multiple events like B1, B2, B3 up to Bn. Okay. Now what are these are different events, and one major condition is given here. So when we can apply this theorem of total probability, that condition is that if if B1 comma B2 comma B3 up to Bn be a set. Okay, so basically all these are a set which is a mutually exclusive set, or you can say they are part of a set and these events are mutually exclusive. Mutually exclusive events, these are mutually exclusive events and exhaustive also. Clear? So what do I mean? Let's understand this. Let me give you one example. That way it will be very easy for you to understand. Carefully see this. Let's see what is this B1. Let's say you have a sample space. You have a sample space, or you can say you can indicate it by B also. Carefully see this. B. Let's say the total possible outcomes you have in this sample space is total is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So total 10 possible outcomes are there. This B1 is having numbers from 1, 2, 3. This B2 is having numbers from 4, 5, 6. And this B3 is having the numbers 7, 8, 9, and 10. Okay, clear? Now, if you carefully observe, if you focus on this particular statement, can I say all these events? So here in this example, I have just considered 3 events, B1, B2, B3. Now, if this is these B1, B2, B3 are part of this particular set, as you can see that B1 is having 1, 2, 3, this is part of it. B2 is having 4, 5, 6, part of it. B3 is having 7, 8, 9, part of it, right? So can I say all these events are mutually exclusive events? Just say yes or no. B1, B2, B3, can I say all these 3 events are mutually exclusive? When I say mutually exclusive, what does that mean? That means there is nothing common between them. If you take the intersection of B1 intersection B2, you will be getting 5, right? That will be 0, you can say, or 5, right? Similarly, B1, B2, B3, if you take the intersection of all 3, again, there is nothing common here. So can I say these 3 events are mutually exclusive events? Yes, the answer is yes, these are mutually exclusive events. Okay, what else? Can I say these 3 events are exhaustive also? Why I can say these 3 events are exhaustive? Okay, so before that, if I say mutually exclusive, I can say B1 intersection B2 intersection, that is equal to 5. This is what do I mean by mutually exclusive. Okay, when I say exhaustive, so exhaustive means if you consider all 3, that means if you take the union of B1, B2, B3, can I say it will be equal to B? That means the total sample space. So this means that they are exhaustive also. Is this clear? If this condition is there, this condition has to be there if you want to apply this theorem of total probability or law of total probability. If this condition is not there, you cannot apply it. Is it clear? Any doubt, anyone? Okay. So when this condition is there, what this theorem of total probability says, when this A is an event caused by all these events, mutually exclusive and exhaustive events, then we can say this, that probability of A, can I write like this? The probability of A is nothing but probability of A intersection B1 plus, because A is an event associated or caused by B1 also. Similarly, it is caused by B2 also. So plus probability of A intersection B2 plus probability of A intersection B3. Yes or no? Correct? Is this clear? Any doubt, anyone? Visually, you can carefully see this. If I say, let's say this is my B, this is my total sample space B, right? Now, if I say that this is my B1, This is my B2 and this is B3. Now, can I say this diagram are mutually exclusive and exhaustive? Because if you take the intersection, it is 5. If you add all of these, now this A is somehow you can represent like this. Correct? This is my A. This is my A. Now this A is an event caused by this B1 also, right? Caused by B2 also, caused by B3 also. So if I have to find the probability of A, then you can clearly understand in this way that probability of A will be nothing but probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection B3. Now the same thing, now you know this. These things, you know the multiplication, so there is a law of multiplication. Carefully see this. We are going to use this one. If I'm writing like this, A given B, probability of A intersection B divided by probability of B. This is our conditional probability, correct? Now what this law of multiplication says, so here you can write like this, probability of A intersection B. You can write like this, probability of A given B by probability of B. Yes or no? We can write like this, correct? Now we are going to use this law of multiplication, and I can write like this. Carefully see this. Probability of A, you know that this is probability of A intersection B1. So can I say, I can write like this, that it is going to be equal to what? It is going to be equal to probability of B1 multiplied by probability of A given B1 plus probability of B2 multiplied by probability of A given B2 plus probability of B3 multiplied by probability of A given B3. Do you have any doubt in this one? Anyone, please ask if any doubt is there. This is what? This is your law of total probability. This is the law of total probability. And when this is possible, when this condition is there, when this condition is there, this must be there. This condition must be present. Then only you can apply this theorem of total probability or law of total probability. Otherwise, you cannot apply. Okay. So can I write this now? Like if I have to generalize this, can I write like this? Probability of A is summation of summation of P of Bi multiplied by P of A given Bi, and I is ranging from 1 to n. Yes. So this is how we can generalize this as well. This is how we can generalize this as well. Correct? This is what is your law of total probability. Any doubt, anyone? Okay, now let's take some example. So where it is? Yeah. So here let's take this example. So if I say these are the events B1, B2, B3, and let's say A is event that is associated with this, and let's say the outcomes that we have in this event is maybe all the numbers, let's say divisible by 3. If I say all the numbers divisible by 3, what will be the possible outcomes in A? Can I say 3, 6, and 9? Yes or no? Let's say A represents one event where the numbers are divisible by 3. Clear? So A is, let's say, so divisible by 3, that means 3, 6, 9 will be there. Now, if I have to find probability of A, that means the probability of an event or getting one number out of the total one that is divisible by 3. So how can we find it out? Can you do it directly? Can you tell me what will be the probability of A? Final answer directly, just by seeing this. 3 by 10, right? So total outcomes for this event is 3 and total sample space that you have is 10. So 3 by 10, that will be your answer. But let's try to verify this. Let's try to verify this through this one. Now just tell me this, sir, length of this lecture. It will max like 1.5 hours. not more than that. Just after that, we will be solving 1 or 2 more questions. Okay. So every day I will be taking 1.5 hour session, not more than that. Okay. Fine. Now let's try to verify this. So probability of A, if I have to find out, so can I say this, that we know that probability, it is also equal to probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection B3. Correct? So now, what is the probability of A intersection B1? Yes. A intersection B1. What is the probability of A intersection B1? Only one is common, right? You can see here 3 and 3. Only one is common. So can I say it will be probability of A intersection B1 will be 1 by 10? Yes or no? Similarly, probability of A intersection B2. So only one thing is common, that is 6 and 6. So only one possible outcome out of total sample space. So again, it is 1 by 10. And here also it is going to be 1 by 10. So total I will be getting, that is 3 by 10. So can I say that this theorem of total probability is applicable here? Correct? Okay, understood. So sometimes we can apply this one directly, and when sometimes you cannot apply this one directly. Why? Because if the information is not given in this way, like we are going to solve one question. So let's see this, and then you will see that sometimes you have to apply this formula to get the answer, right? That means using the law of multiplication. So this is just theorem we have. You can just explain it here. So, fine. Now let's solve this question. Do you want to solve this question now? Quickly, everyone, and let me know what should be the answer. Give it a try. So the question says, we have boxes, each both, and box 3, 4 red balls, 1 blue ball. Now I want to pick about, can we apply theorem of total probability here? Tell me yes or no. Because if you are analyze the problem properly, but it is important to understand where apply of total probability, where not apply. Okay, so let's understand this. So you have box 1, box B. In box, what do you have? Red ball and balls. Have 2 red and 3 balls. You have red one. Now I'm once propertable and visible. Just no. Am I and visible? Better? Okay. I work. Okay. Just let me know when it is working fine. Okay, let's see this now. So in box B1 we have this, box B2 we have this, and box B3 we have this. Okay, now do you have, let's first understand this one. Can I say all these three events, B1, B2, B3, can I say all these three events are mutually exclusive and exhaustive? The first condition, you have to ask yourself whether these three events are mutually exclusive and exhaustive or not. So you will find it out that there is nothing common, right? This box is separate, this box is separate, this box is separate, right? So this is mutually exclusive. But what about exhaustive? Yes, they are exhaustive also. You add all these balls, so you will be getting total balls, correct? Total red balls and total blue balls. This is exhaustive also, fine. Now we want to find the probability that you pick a red ball. Now picking a red ball, can I say picking a red ball, this event is associated with all three boxes? Why? Because in all three boxes, ball. So can I say this event A is associated with all these three events? So now you can clearly say that yes, we can apply the theorem of total probability here. Okay, so theorem of total probability can be applied here. So find the probability of A. Let's say A is an event of picking a red ball. Fine. So this probability of A, can I write like this? It will be equal to probability of B1 multiply probability of A given B1 plus probability of B2 multiply by probability of A given B2 plus probability of B3 multiply by probability of A given B3. This is what? This is our theorem of total probability, right? Now, just tell me this. What is the probability of B1? Probability of B1, that means picking a, choosing a first box, right? So can I say probability of B1, probability of B2, probability of B3, all are equal to 1 by 3 because there are three boxes. So first you have to choose which box, first you have to pick a box, right? From that certain box, maybe it can be box B1, B2, B3. So first you have to choose a box, and then from that particular box, you have to pick a ball, right? So probability of B1, B2, B3 will be equal to, all will be equal to 1 by 3. Okay. What about probability of A given B1? Now, this is conditional probability. We are finding probability of picking a red ball, and it is already given that chosen box B. Chosen box B1 of picker. Set is 3, total 5. Again, lag is there. Okay. I don't know why it is happening because it's working fine from my side. Maybe some speed issue is there. Just a minute. Yeah, it is more than 100 Mbps. Now it seems fine. Okay, fine. Let's continue. Sorry for this lag. See, I'm at home, so I'm not in Bangalore. So here I have just one Wi-Fi connection. There I have multiple connections. So there this issue, does not happen. But it's okay. Like we can manage, right? We can manage. So I hope now it is fine. So probability of A given B1, that means probability of picking a red ball given that we have chosen box B1. Similarly, probability A given B2. What will be A given B2? So it is already one that you have chosen. So probability of picking a red ball will be 2 by 5, right? It is going to be 2 by 5. And what about probability of A given B3? So that is going to be what? It is already given that you have chosen B3 box, so it is going to be 4 by 5. It is going to be 4 by 5. Is this clear? Do you have any doubt in finding these probabilities? All clear now? Okay. Now all you have to do is substitute. So probability of B1 is 1 by 3, multiply probability of A given B1, that is 3 by 5, plus probability of B2 is also 1 by 3, probability of A given B2, that is 2 by 5, plus 1 by 3 multiply 4 by 5. Now if you solve this, what do you get? So this is going to be 3 by 15 plus 2 by 15 plus 4 by 15, and that is going to be what? 9 by 15. So 9 by 15 is the correct answer for this one. Is this clear? Yes, Chandana, your answer is absolutely correct. Sumit, I think you have committed some mistake, silly mistake. Is this clear? Any doubt, anyone? So are you getting the idea how you can find out whether law of total probability can be applied or not? Theorem of total probability can be applied or not. Now I'm giving you one more example. This is the last question of today's class. Try to solve this, everyone. Try to solve this question now and let me know what should be the answer. Again, ask the same question to yourself, whether total probability can be applied or not. Okay, do it. And just make sure that you don't commit silly mistake. Yes. Understood the question? See, the question is saying a bolt is, let's read the question first. A bolt is manufactured by 3 machines A, B, and C. We see, Chandana, it is not talking about what kind of defect is there. It is simply saying it is defective. Okay, let's see this. A bolt is manufactured by 3 machines A, B, and C. So 3 machines are there. A turns out twice as many items as B, right? Okay, and machine B and C produce equal number of items. So there are 3 machines A, B, and C. It also is equal to twice production of the bolt. That means these 2 machines, they produce equal number of items. Now 2% of bolts produced by A and B are defective. Okay, 2% of bolts are defective by A and B, and 4% used by C are defective. Fine. All bolts are stockpile. So in one stockpile, you have put all the bolts used 3 machines, and one is chosen from this pile. Now you have to find what is the probability that it is defective. Now just ask yourself whether you can apply the theorem of total probability here or not. Now, using machines, can I say are mutually exclusive and exhaustive? Why I'm saying so? Because total number of bolts, let's say, I can assume here, maybe I can say A plus B plus C. Let's say if I say, I'm assuming that it is equal to 10, some random number, you can take number also. Now if I say A plus C is equal to 10, now A is equal to 2B, so I can write 2B here, and b is equal to c. So again, it is going to be 2b is equal to 10. So I can say 4b is equal to 10. So ultimately we can say b is equal to 2.5. Similarly, I can say c is also equal to 2.5, and a is equal to, because a is of, right? Really, we have chosen number 10 and we are getting in decimal. That doesn't make much sense, but yeah, it is kind of net, so we can take it. It's not an issue for us. Is this clear so far? Is this clear so far? So these three machines are producing or manufacturing the bolts. So I can definitely add beginning bolts. Yes. So they are exhaustive, and all three machines are producing the bolts. So it is same as, the same example you can consider as three bags are there and some balls are there. So you are just adding into one single bag. So yes, you can say that they are mutually exclusive also. Now, you need to find the probability that it is probability that by D. So probability of D you need to find out. So can I say, I'm sorry, the probability of D, nothing, I say of A multiply by probability of A, probability D given A plus probability of B, probability of D given B plus probability of C, probability of D given C. What does that mean? That means probability of A, and here it is conditional probability, probability of bolt is defective given that it is manufactured from device or machine A, right? This is what it says. Fine. Now, what is probability of A? Anyone? What is probability of A? See, A is equal to 5, total sample space is 10. So can I say probability of A is 5 by 10, or you can say 1 by 2, correct? What is probability of B? 2.5 divided by 10, correct? Or you can say it as 1 by 4, yes. Probability of C is also same, 1 by 4. So this thing we have found out, okay? What else? If I ask about probability of D given A, that means the bolt is defective given that it is manufactured from A. So 2% of bolts produced by A are defective. So can I say it is 2 by 100? Clearly it is given, directly it is given to you. Probability of D given B, that is also 2 by 100, yes or no? Because 2% of bolts produced by B are defective. And probability of D given C, 4% of bolts produced by C is defective. So 4 by 100. Is this clear? Any doubt, anyone? Now simply substitute the values. So probability of A is what? 1 by 2, right? 1 by 2 multiply by probability of D given A, that is 2 by 100 plus. This is 1 by 4. This is 2 by 100 plus. This is 1 by 4. And this is 4 by 100. Now if you solve this, what do you get? So 2 by 200 plus 2 by 400 plus 4 by 400. Like you can take LCM, or directly you can just multiply by 100 also. That is up to you how you want to solve it. Just a minute. Or you can even simplify also if you want to, right? So if you simplify, this is what you are getting. So basically, if you add these two, it is 2 by 100 plus 1 by 200. This is 2, 4, and this is 1. So this is 5 by, just a minute, let me write it here. So this is 5 by 200, and that is nothing but 1 by 40. So that is your answer. Is this clear? Any doubt, anyone? I hope it is crystal clear to all of you. And you may get question from this theorem of total probability in your gate exam also. Okay, so I hope now you can handle any type of question based on this, right? The next topic that we are going to cover will be Bayes theorem, and that is the foundation. That is the main, I can say, theorem that is going to be utilized in further topics of uncertainty. Because there, after this, we will be talking about Bayesian network. That is the first topic of uncertainty, reasoning under uncertainty, and there we use this Bayes theorem. So next class is also going to be very interesting because we will be solving questions as well, and there will be few more things that you are going to understand. Okay, is this clear so far? So after covering this Bayes theorem, then we can say that we have covered all the prerequisites required for this reasoning under uncertainty. Okay, then we can directly start with the Bayesian network. But to understand the Bayesian network, you need to understand few things that I will be discussing in the next lecture or in the next to next lecture. Okay, then we will be starting Bayesian network so that you can get the entire clarity of how it is working and why it is working. Fine. So I hope you enjoyed today's class, everyone. Yes.